Good afternoon, everybody, and thank you for joining for this session on GLIWA on T1 timing analysis. So I will just start with our company Trident InfoSol introduction. So Trident InfoSol was in the was inception in 2000. We are almost 25 years we have completed, and we have we are the AS 9100 and Semilex certified company, and we have the solutions from main product solutions are divided into two parts: embedded hardware and the engineering software. And we have more than 200 people over the locations, and we are the complete solution provider, and we are catering to almost all the industries which are tend to use these kind of products. Our main operational office is located in Bangalore, and followed by our corporate offices in New Delhi. And we have our other sales and tech operational office located in Mumbai, Pune, Hyderabad, and Chennai as well. So as what we do, we are, right from the conceptual stage to the product design to the prototyping and integrated system development, we provide all these solutions that you can see, right from the requirement capture to the embedded code development to the COTS hardware and to development the rugged racks and consoles for the different product applications. So this is a brief information about embedded system which we are manufacturing in-house. So these products are mainly goes for the avionics application for in-flight as well as ground test application, where it requires stringent military certification like MIL standard and other certifications. So these products, as a Make in India initiative, we are manufacturing in-house. But from software, let's start from the software. So as I told you earlier, all the software we are from right from the conceptual stage to the production stage. Whatever the tools are required to qualify the product we have. So you can see right from the requirement analysis to the model-based engineering to 1D simulation. We have tools from our OEM Dassault systems, and then we have for the coding and prototyping of your C code, we have the multi-ID compilers from Green Hills. And for the reliability prediction and for the MTBFs and other things, we have tools from ALD. And anyways, GLIWA, we have the T1 timing analysis and all. And for hardware in the loop simulation system, we have a tool, we have a hardware from Speedcode, which is a sister concern company of MathWorks US. So these are our brief information from clientele. As I told earlier, we are catering to almost all industry sectors, right from the government to the commercial sectors. From government, we are catering to all defense organizations like DRDOs and space ISROs and defense PSUs and all. And for the commercial, we are catering to almost all customers from the tier 1 industry OEMs, from the automotive to industrial to other things. This is just a small intro of GLIWA. So GLIWA and Trident have been closely working with major customers for providing the state-of-art advanced timing analysis tool. So how GLIWA works, it gives you a timing analysis, give you the information on the timing measurement and on the target side timing verification, automotive timing test. With respect to the automotive standard ISO 26262, it also gives you the certification for that one, as well as for the implementation of AutoSAR and other related stuffs. And also it also gives you the information on the data flows and the event change and the synchronization effects in multi-core projects. Also, you can do the tracing of timing and functional problem without halting the target, particularly valuable in multi-core projects where it may be impractical to halt a single core. So this is just a small intro of GLIWA. Anyway, my speaker, Mr. Christian, will take you a detailed session on the GLIWA tool. So let me introduce to Mr. Christian. So Christian Wenner holds a German diploma in computer engineering and British master's degree in distributed computer system engineering. He earlier worked in Daimler Crystal, which now called as Mercedes-Benz, and Bosch and other automotive development companies before joining GLIWA in 2015. He also teaches some university courses as well. And he has been continuously involved with customer projects since then, and as a first field engineer today as a director of training and coaching. So maybe I will transfer this after this. Maybe Christian will take over to this session. Anything related to any technical or commercial thing, you can directly mail to info@tridentInfoSol.com and you can directly contact. So our people will direct to the concerned sales representatives. So over to you, Christine, for this session.
Thank you very much. So good afternoon, everybody. Let's share the screen and make sure it's the right one. Okay, you should hopefully now see a title slide.
Yes.
So today we're going to take a look at the timing in automotive projects and the do's and don'ts, and also peek a little bit into the tooling that's available from GLIWA, the company I work with. After a short introduction today, where I'll share some motivation why timing matters and do a very, very brief, okay, who is GLIWA, who am I, and what is T1, we will jump into the timing basics, basic but still very important. We'll take a look at the task states, at timing parameters for measurements and showing whether your system is healthy, requirements, which will refer to these parameters, the definition of what is CPU load and strategies to deal with it, and then there will be a brief demonstration on how you can do these things with T1, and hopefully there'll be some time for questions and answers. So here's the management summary. Why do we care about timing? We care because if you need a safe and highly reliable embedded system, the timing has to be in order, among other things. We care because many projects run into timing issues, overloaded systems, but still more functionality that needs to be added, sporadic crashes, weird functional behavior, communication issues, that kind of stuff. It's often not clear that the root cause is timing. And then that leads to problems which can be avoided by optimizing and monitoring the timing soon enough, which can also save you money. There's an example. Okay, it says my book. It is the book of my boss, Peter GLIWA. Sorry about that. His name is on here. Yeah, it's one of the stories from a real automotive OEM who managed to keep an old microcontroller for one more ECU generation, which served a lot of money. So that's the management summary. Why is timing important? Now, the very brief intro for the company and myself. We've been at it for 20 years, going on 21 now. We are operated by the owner, Peter GLIWA. We are a member of AUTOSAR, which is an automotive software development standard organization. We do timing stack memory analysis. We're about 60 people. And here's a bunch of customers. And that you've all heard. The one thing you may not have heard yet is that I also once was the document owner of the technical report timing analysis within AUTOSAR. Okay, enough about me. So what can you do with T1? Well, you can visualize timing and measure timing. We'll take a look at what the differences are later. You can verify timing, debug and optimize. And the very nice thing is you can use it on your development desk. You can use it in the lab. You can use it in a hardware in the loop environment. And you can use it on a test track or in production or even on public roads. That's the ISO 26262 aspect of it. Also, there's stack analysis and memory access prediction. But now let's take a look at embedded timing as such. What is it about? Enough about tools. Let's take a look at the reality we face. So you've all seen this probably. It's the letter V, and usually when it's painted like this, it's about the development model, the V model. And you start on the top left with your requirements, from which you derive a design, from which you derive implementations that you integrate, and then you do module tests, and then you do system tests. And today, the first point I'd like you to take home is always keep thinking about timing too when you're doing an activity. So when you're doing requirements, also think about timing requirements. Okay, this piece of code has to do this, but how fast does it have to finish? Is there a limit? And in the design, Think about timing in the design. Which task do I put this in? How often does this have to run? Do I have to optimize it, or does it not matter? And when you implement things, start measuring timing as soon as possible, because then you know. And when you do module tests, which you need to do anyway, measure the timing while you're doing them. And then you know, A, is it functional correct? And B, does it finish as quickly as we intended it to? And with the system, that would be profiling on system level, response time, CPU load. We'll dive into the details in a moment. Okay, so you got your metal box. Inside is a microcontroller. In case of an automotive project, it will probably be an AUTOSAR compatible operating system, which runs tasks. How do these work? They start out in the suspended state, which means the task is not running and it doesn't want to run. Then there's an activate event, which will tell the task to become ready to run. And then the operating system will start the task, at which point it's actually occupying the CPU, foreshadowing the CPU load topic here. This is where CPU load happens. And sometimes your task gets preempted before it can be done by something higher priority, which takes you back here. And then it goes up here again and down here, and eventually it will terminate, at least if it's basic conformance class, which is the most reliable class. So ideally, whatever you can handle with these, please do so. Then there is the extension, extended conformance class, which allows you to go from running into the waiting state by calling wait event. And then the task will sit here until the event happens. It will then be released into the ready state, from where it can go back into the running phase. This adds a lot of potentials for things to get stuck in a way that you do not immediately recognize. So we generally advise people to use extended conformance class and events sparingly. If you need to, go ahead. But if you don't need to, it can get you into a lot of trouble that can be really tedious to debug. So don't make things more complicated than they need to be. And ECC often is more complicated than it needs to be. Which takes us to timing parameters. So we have these task states, and you will see the same colors here. Light green means it's ready. Dark green means it's running and occupying the CPU. And if we put a few of them together, then we get situations like these, with a lot of timing parameters over here, which describe certain aspects. All of them are useful in certain use cases. Today is not enough time to go through all of them in detail. I'll just pick one or two examples. For example, if a task gets activated, but it does not immediately start to run, this is called the initial pending time. And it's an indicator that something higher priority up here is keeping this task from running at the point in time when your schedule says it should be running. And that's already an early warning indicator that something in the system design is suboptimal, because every piece of software in this task that relies on the idea that it's running at this point in time will be disappointed, and its output will be delayed, which can have a cascade effect. So that's the initial pending time. And another really important aspect is the dark green sections are called the core execution time. That is what goes into your CPU load. The time from start here to termination back here, this is called the gross execution time. This is how long it takes. These are how much CPU time it takes for its operation. Two completely different things, important to keep apart. Also, these are not names that we came up with at GLIWA. I can show you them here. In the official AUTOSAR timing document, you set the same task states, and here are the very same parameters. So it's a good idea to learn these because it allows you to talk to other suppliers, vehicle manufacturers in a way that everybody immediately understands what it's about. How do these timing parameters then tie into requirements? Well, here's Paul. And Paul's a function developer, creates a software component, which is like a class in AUTOSAR, with a cyclic runnable that runs every 10 milliseconds or so, and a nice control algorithm, reads data, performs mathematics, outputs something else, closed loop control. And Paul states that the thing shall run every 10 milliseconds. So now we have a requirement for the delta time parameter. And is it all good? Nope, because the actual delta time will be subjected to jitter. And if Paul designed the thing to work at exactly 10 milliseconds and your real system cannot deliver the exactly 10 milliseconds, this is what he wanted to get. And if his algorithm is robust enough to deal with 8 to 12, you will get it. And if the algorithm absolutely needs exactly 10, this is what you get. And the weird thing is, if you look at the mathematics, if you run model-based tests, it will be perfectly fine because the math is perfectly fine. But the dirty reality is it's never 10 milliseconds. That's just one example how these kinds of timing problems can get you real functional problems, where if you review the code, there's nothing wrong with the code. You can even prove that the math works out, but the assumptions are violated. Okay, how would you measure timing? Well, old style, you would just set a pin when your task starts and you would clear your pin when your task ends, which works quite well. And then you hook up an oscilloscope and you can see how long it runs. The thing is, you can also do that in software. You read a timer value here at start, you read another one at stop, and then you just subtract those two. And there's your gross execution time. What happens if something happens in between? Well, you would get something like this, an interrupt service routine, and that will not be part of the gross execution time. The GET will stay the same, but now the amount of time, real CPU time burned, shows up here and up here. And if you're the person responsible for this task, it's not your CPU load. So it's important to keep these aspects separate. And with T1, you can measure both. Okay, so I've been saying CPU load a lot. Let's take a look what it actually means. There's an expectation linked to CPU load. Managers love it. It's a number, it goes into the requirement document, and you have to deliver. It turns the entire complicated scheduling and timing world into one singular number. Beautiful. You can even derive a traffic light and say, oh, okay, greater than 85% is red and 70 to 85 is yellow and less than 70 is green. Wonderful. However, the reality is a bit more complicated. So this is the expectation for CPU load, but engineers might have their own opinion on that. But it's a valid thing and people demand it. So we need to take a look at how it works. Let's take this expectation and see if we can find a way to calculate the CPU load in a reasonable manner. By the way, AUTOSAR does not know the term CPU load. Okay, here's a formal definition, and I don't want to bore you with math, but it's pretty simple. Basically, the total execution time is the sum of all core execution times of everything that runs, and there you are. Now, important, of course, is what is everything that runs. Usually it means everything that is not your idle loop or idle task. Everything that's not in there is considered work, and here's the sum of all the work. Then we take the sum of all the work that we observed in a certain time frame, divide by the time frame, and we get a dimensionless number between 0 and 1, which is usually expressed in percent. Pretty straightforward. Well, let's take a look at an example. We got 3 tasks over here, and here's our time axis. And if we just project these down, we get this line, which is basically a CPU busy line. And as you can see, there are different situations. Now we get ourselves an observation frame from here to here. That's the T0 from the previous slide. And now we can say, okay, the observation frame is 12 boxes long, 7 of them are occupied. That's 58.3% CPU load. Wonderful. But if you take the same observation frame and apply it at different places in this situation, we can see that this one is the 58.3 that we just talked about, but then the next one right after it would be 83%. And then here's the guy with 50. So the question is, which one is right? Well, ideally the one that can get you into most troubles. So it's highly advisable to pick the maximum, because that is the situation you need to look at. Now, how does this look in reality? Here's a trace recorded with T1 for a real ECU from a real car manufacturer that is by now 15 years old, and lots of them are out there on the streets. And these are the real tasks. So if we take an observation frame of 50 milliseconds from here to here, and then from here to here, we get a maximum CPU load in this area of 72.19%. And we call this observation frame the basic scheduling frame, which is defining that T0 time span. Now we change it to a small observation frame, and notice how it's the same trace. I can switch back and forth. And if you look at the trace and the events, it's exactly the same ECU, same situation, same software. But now, just by switching the BSF event to be 10 milliseconds, the resulting maximum load is now 85.39%, and it's happening here. So there's a huge difference between a big and a small observation frame. Which one do we choose? Well, that's a non-trivial question, so let's take a look at it. We got 3 cyclic tasks in this example, 4 milliseconds, 8 and 16, and they run for certain amounts of time. And then there is this very slow running 1000 millisecond task that does some background activity. Here's our time scale. And here we get a failed task activation. A failed task activation means the 16 millisecond task, which happened here, needs to again run here, but it wasn't able to finish. It was still doing work, then it was suppressed by higher priority things all the time, and now here it fails. That's a real problem. If we project the CPU load down here, then we can say, okay, if I take a 2-second observation frame, if I take the entire thing, I'm below 70%, yet still my system fails. That is too long. What if I do 1 second? Still 69%, still too long. What if I do 16 milliseconds, which is the slowest cyclic task? I get 75, 68, and 100. Aha, now this 100, that's really a strong warning that something isn't right. So this, for this situation, is a useful observation frame. And then if we go to 8 milliseconds, we still get 100 back here. And if we go to 4 milliseconds, we start to get issues in the opposite direction because we get 100 here and 100 here and 100 here. It's like the fable of the boy who cried wolf. This is alerting you too often when there's no reason for it. And if we go to 3 milliseconds, basically everything degrades. So the answer is, like with so many things, pick a reasonable thing in the middle. A good guideline can be take your slowest cyclic task that does real important work and see if that is a suitable observation frame for you, or maybe go one faster. Okay, so much for the CPU load. We got a few minutes left, so let's take a look at how this would look on a tool level. I've got a target here on my desk. It's a triple core Infineon Oryx. This is T1 when you launch it and load a project. I'll connect to the target using the CAN interface. And here are CPU load numbers. And as you can see, they dance around a bit because basically we show a floating average over a few seconds and keep updating that. The gray area, if you can see it on your screens, is the values that were observed. And the red flags are warning levels that you can set that will trigger an immediate reaction where a C function callback will be called that you can fill with your own content. Enter a diagnostic issue, turn on the red lamp, whatever makes sense for you. Under this, we have a statistics area that shows you timing parameters, exactly the ones that we talked about before. These guys, core execution time, cross execution time, response time. By default, you get the maximum observed core execution time, so the highest amount of CPU that any one instance of these tasks, and in this case, interrupt service routines, ever used. But you can tell the system to give you other information, like I want to know the delta time. Is my 1 millisecond task really happening every millisecond? And as we can see here on this demo project, the 1 millisecond task has a delta time that bounces around between 900 and, okay, now it's 898 microseconds, so 0.9 milliseconds, and almost 1.1 milliseconds. So already we can see there's a 10% jitter. Doesn't have to be a problem, depends on what kind of software you have in there, but it's definitely something you should know about the behavior of your software. Here are the periods for my tasks, but what are the real delta times? And you can also select the others, like the response time, which is the time from activation to termination. Control loop people are very interested in that because usually your input data arrives just before activation. And then you want to know how long until all my mathematics are done, all my calculations are performed on that data and the outputs are calculated. If it takes too long because your routine gets interrupted and preempted too much, then maybe your control loop quality suffers, even though your math is fine. If you're working on stale, outdated sensor data, then obviously the quality of your closed loop control is going to suffer. This is the statistics. And the other really big thing is you can download the raw events that are happening on the microcontroller. Now you saw that this download took around 5 seconds because I'm using CAN as the target interface. With an Ethernet target, the thing will be done in half a second and things are much faster. We support a wide variety of buses to talk to the target. And when we do the download, we are again met by CPU load. Let me zoom in on this a bit. Now it becomes readable. Okay, good. We have 3 cores. The 3 cores are executing software in different tasks. And here we have the CPU load numbers for our observation frames on core 0, on core 1, and on core 2. And you can see that core 2 tends to have time frames where it's pretty highly loaded. And these bars here are pretty much the projection we've just seen in the slide set. It just tells you, okay, dark green, CPU is busy. Light green or white, the CPU is not running. Or the CPU, of course, is running, but it's running code from the background or idle loop. So this is not considered work because you could put more things on there and it would be fine because there's still a lot of time available in the idle loop. Here, it's not. You can immediately see graphically that there isn't too much space to squeeze things in. So apart from the stats here, we got the detailed trace information for all 3 cores. It's synchronized to one common timeline. So especially if you're looking for multi-core interactions, data consistency problems, locking problems, a topic we will focus on in the second session, which will be in early 2025, then it's really helpful to have a view of what's going on across the core boundaries. And within each core, we can, if we zoom in far enough, see in the same color scheme that was already introduced, the same procedure. Up here is the operating system scheduling interrupt service routine. And we can see how when this is called, let's zoom in a bit more. In this specific example, 2 tasks get activated, the 1 millisecond task here, the 25 millisecond task here. And because this one has a higher priority, of course, that's the one that starts. And this right here is the initial pending time I was talking about. So the schedule says both tasks are supposed to run at this point in time. The 1 millisecond task gets to start after 5 microseconds, but the 50 millisecond task has to wait for 120 microseconds before it can run because it's blocked by higher priority things. In an ideal world, the schedule would be set up in such a way that you do not activate 2 tasks on the same core at the same time, because demonstrably they cannot both start on the same core at the same time. So that's already a schedule design. Well, maybe it's not a problem, but it's definitely something that could be done nicer. And this is what this detail view is about. It allows you to see exactly who is preempting whom, when, under which conditions. And those of you who have some experience with weird effects where software works fine unless there is this one situation with that special amount of bus traffic and certain interrupts arriving at exactly the wrong time, and then things go wrong. This is the kind of view that will help you to see what's going on. In order to support that, we offer a wide range of tools that goes all inside T1, that goes way beyond the scope of what we can do here today. I don't want to bore you to death. There's smart triggers that allow you to trigger on any of these conditions. So I could, for example, say, okay, 1 millisecond task, the delta time here, I want to know if the delta time ever exceeds 1.09 milliseconds, for which I could just go over here to the tasks, find my task. The context menu now opened on the other screen, but You'll see the dialog soon. So here's add constraint. You get this. And basically, if you have a requirement that says maximum allowed delta time between two instances of this task is 1.09, then, well, let's go for 109. And that's what we need, 1 millisecond and 90 micros, maximum threshold. All right, there you go. And now, just like with an oscilloscope with a smart trigger, T1 on the target compares the freshly calculated time against the set limit. It was immediately exceeded, so it stopped tracing, just like an oscilloscope in single shot mode. And now I can download the situation, and I get a big fat red warning that says constraint violation. And as you can see, most of the 1 millisecond task instances are perfectly fine. And then every now and then, under specific conditions, there are the ones that are not. And we can look at the specific case where it happens, and we can see that somehow this variable task is involved here. And back here, also the variable task is involved. So there's a suspect, and that's what we need to investigate. That's just one example. There's 10,000 buttons and lots of stuff. We're happy to show you individually. Talk to Trident Infosol to arrange a appointment, and I'll be happy to show you things. And that's pretty much it. I'd very much like to ask for questions and comments at this point, and thank you for your attention.
Thank you so much, Kristen. There are a set of questions which has come up. Let me take them for you, one after the other. Give me a second, let me read that. So what are the different processors, compilers, and operating systems are supported by GLIWA?
Very good question. The short answer is a lot. The better and longer answer is go to gliwa.com, go to products, and there you'll find supported processors and so on. That is the official list. That is kept up to date. That is what you should refer to. And currently we got lots of Infineon variants with several compilers, Tasking, Hightech, Green Hills, Wind River. We got the PowerPC-based NXP STM chips. We got not everything from ARM. There is just too much from ARM, but a lot of these things from ARM. So Cortex R series, the real-time chips. Cortex M, the typical microcontroller things there. We basically support everything, including Raspberry Pi Picos. We have a YouTube channel, and there's a video I did about Picos. And yeah, RH850, and if you're into digital signal processors, the C66X series of Texas Instruments. Others can be made available. We are basically porting the things if and when people need it. So if your thing is not on the list, talk to Trident, they will talk to us, and if it's doable, we can just add it.
Okay, thank you so much for that answer. Let's go to the next question. What is the granularity or the smallest of time measure? Is it in milliseconds, microseconds, or nanoseconds?
Excellent. That's exactly what you need to know. So internally, we are reading timer values. T1 is a software-based solution, which means you're not plugging in a hardware tracer. So everything happens in software with all the pros and cons. How fast does it get? The answer is A, how fast is the fastest timer in your system? So this is a 200 megahertz Oryx, and potentially we could use 200 megahertz timestamps, which would give us 5 nanoseconds per tick resolution. If you click on the system here, then you can get the tick resolution down here, and indeed there it is, tick resolution 5 nanoseconds on this chip. There is one caveat. If the timer overflows too quickly and there is no trace event in between, you get aliasing problems. But our field application engineers will make sure together with you that that doesn't happen. So 5 nanoseconds is no problem. If you have a faster chip, you can even go faster. But for the details, please contact our technical personnel.
Thank you so much. There is another question from Puneet. What is the limitation of GLIWA if we compare it to hardware-based debuggers in the market?
Let me see if I can find a comparison table for that. But while I'm searching, I'll already start telling you things. So basically, you can expect more detail from a hardware trace because the hardware tracer can give you more events per second. It will give you more detailed insight, and it can provide you with things like instruction timing. So here we are, and that's of course reverse. So there we are. T1 can do certain things, hardware-based tracers can do certain things, and there's a certain overlap. Basically, so yeah, there's the hardware tracer. I'm looking for the, I don't have the table. The hardware tracer will give you better resolution and more detailed results. If you're looking to profile a short piece of software and you want to know down to a very specific level, how fast is my inner loop, how much latency is on that specific memory access, the hardware tracer will be the way to go. If, on the other hand, you are more focused on, okay, what's the state of my tasks and interrupts on that level without looking at detailed code sequences, then I would argue T1 gets you the results quicker, because with the hardware tracer, you need to record millions of instructions and then you need to post-process that to get your task states. With T1, you get it immediately. And the other big difference is the hardware tracer needs a chip that is capable of talking to it, usually called an emulation device. That's usually not your production device that goes into the car at the end. And the pins need to be available, and you need the cable, and you need the hardware tracer. If you're a developer who has this A sample hardware on their desk with a nice hardware tracer, that's beautiful equipment and you will get excellent results from it. If you're more of an application test engineer who takes a C or D sample into a car and goes onto a test track, and the thing is mounted in the engine compartment and everything is shaking and getting hot, usually there's no way to use a hardware tracer. At that point, you would use T1. And yeah, we typically tell our customers, if possible, use both, because the use cases are slightly different, and depending on what you do, one or the other is better.
All right. Thank you so much. We have a question from Silva Kumar. The question goes like this: can T1 be used in legacy architecture?
Well, it of course depends on what exactly that legacy architecture is. Currently, for example, we do not have the 8-bit Atmel AVR listed in this table. A few years ago, it was listed. So we definitely have a T1 target software archived, an old one, but it's tested and working, that would immediately run on an Atmel AVR, which I would consider legacy. The design is from the 1990s. Basically, we can adapt most of the core functionality for any target as long as you have a working compiler that's C89 compatible, a bit of RAM to hold the buffers, and a at least 16-bit free running timer, and something to talk from the microcontroller to whatever records your measurement data. Can be a UART, can be CAN. Ethernet, of course, is fine, but if we're talking legacy, you rather think UART or CAN or maybe SPI. So the answer is Probably yes, but if you want to know for sure, please submit your legacy wish through Trident to us, and we can find out, do we already have it and it's just no longer on the website, or would we need to port, and how long would that take? But in general, the answer is absolutely yes.
Okay. The legacy, what Silva Kumar meant was in the sense of software architecture, other than AutoSAR.
Okay. So basically, we do not depend on AutoSAR operating systems at all. We do not depend on AR XML AutoSAR specifications. Absolutely not. What T1 needs on the target is a place where somewhere in, if you use an operating system, FreeRTOS or a self-written one, or just a simple scheduler where you have some function pointers and you go through the list, there will be a point at which you start, let's say, a piece of code that you consider a task or a time slice or whatever you call it. And at that point, when that thing gets started, there has to be a call to a C function called T1 trace event, which you then pass your task or time slice ID and the fact that a start event has just taken place. And then when the thing ends, you do the same thing with a stop event. You do that for every task and every slice. You do that for every hardware called interrupt service routine. And that's it. It will work. And our field application people will assist you if necessary. So yeah, absolutely no dependency on any big official AutoSAR stacks. You can run it with self-written schedulers, with older operating systems, or completely bare metal if you want to. Absolutely no problem.
Okay. There's another question from Puneet. Since GLIWA uses CAN bus to get the trace, how much additional load will add on the CAN bus?
Yeah, so CAN bus is an option, and it's what I just used. I just grabbed the target that was sitting next to my desk. We can also do Ethernet and other stuff, but let's talk about CAN. Basically, there are two scenarios if you use CAN. Scenario one, you, our customer, already has a measurement, development, or debug CAN on their ECU. So a CAN that will not be there in series production, but that you can use in the lab and that runs no normal application traffic. That, of course, is the best case. Then we can just dump all our data on there. The tricky part is when you don't have that, when our transmissions need to coexist with your application CAN frames and not disturb anything. That's a typical use case for many of our customers 10 years ago, more often than today. And because of that, you, the user, can choose the maximum amount of bandwidth that will ever be used by T1. The way it works is the target will normally only send messages if the PC requested them. And the target has a rate limit that you can choose at compile time. So for example, you could tell the target to emit only one CAN frame every 10 milliseconds. And then you can do the math and you will see it ends up in a single digit bus load on the CAN, but you could also do one CAN message every 100 milliseconds. For the statistics updates that we're getting here, sorry, let me remove the constraint. So we can re-enable tracing, delete constraint, off we go. So while this is running, if I reset these numbers here, you see we are getting fresh ones, we're getting fresh numbers, and they come over CAN, and they are just calculated numbers. So for this, it would work quite well if you send one message every 100 milliseconds. The update would be slower, but it would work nicely. For this, if I download the trace, with one CAN message every 100 milliseconds, you can expect 2 to 3 minutes download time. But the bus load will be extremely low. So the short answer is you tell us what's acceptable and we can adjust some tuning parameters to stay below that level. And we'll show you where the parameters are. So if you want to change them for special tests, yeah, change a number, recompile, and you're good.
Okay, thank you, Chris. We have multiple more questions coming in. However, let's take the last one for the day. The question goes like this. Can we debug our application by setting a software or a hardware breakpoint?
Is the intent of the question to ask whether T1 can replace a classic debugger, as in really halt the code? Or is the question about, I have a debugger, I may need to halt my application. Can I do that while T1 is running?
Yes, I think the second option.
You think the second option? Okay, then very briefly about the first. No, T1 cannot stop execution on your ECU because it's designed to not do that. It's designed to observe without interfering as much as possible. Now, for the second question, that is a very valid use case that many of our customers need. It depends on the specific chip that you are using. Well, it depends on the chip how much you can do. If everything I showed you right now would also work if I had a debugger hooked up, and if I would set breakpoints and debug two things. What could happen is if I stay in a breakpoint for too long, the PC software would eventually start complaining that it cannot talk to the target anymore because the target is halted. But then when I resume it, it will say, oh, the target is back. Okay, here you are. There is a special functionality called T1 Flex, which is extremely powerful, and I haven't shown you today because time. But there's a video on our YouTube channel if you're interested in Flex. And Flex allows you to do certain stuff with T1 where you usually would need a debugger, like observe memory accesses and trigger on, hey, if to this variable there's a write access and that write access writes a number that is larger than 65,000, then trigger a trace stop. That's similar to a breakpoint. If you want to use that functionality and a plugged in and running hardware debugger at the same time, it strongly depends on the chip architecture and partly on the debugger vendor. A very good example would be the Infineon Oryx architecture, TC2XX, TC3XX. If you use a Lauterbach debugger, that works perfectly. You can basically say, okay, there's 8 breakpoints in total. 4 of them shall be available for T1 and the other 4 for my debugger. And then Lauterbach and our software talk to each other and they agree who uses what. And it all just works in parallel. And at the other end of the spectrum, there are certain power PCs where it will never, ever work because the hardware just doesn't support it. So for your specific use case, please inquire and we can give you a reliable answer. But it's possible in general and we have customers doing it.
Okay, thank you so much, Kristen. And thank you so much for everyone joining this wonderful session on Master Timing for Automotive Excellence. So before we end the session, I would like to just keep all of the audience posted that we do have the part 2 of this webinar on mastering timing in multi-core automotive software, planned to be held on January 30th. So all audience who are interested in the session can please do register. The registrations link or the registration line would be open from next week. So please do register. Thank you, Kristen, and thank you everyone for joining the session.
Thanks, Praveen. Thanks, everybody. Have a nice day.